Hello and welcome back everyone to our live streams here where we develop all sorts of things, and this time once again we're doing operating systems. And well, specifically we're going to look at a feature that you find in much of the modern hardware that we have, if not most of it, that we use on the desktop systems and such that we have, and server systems, and that is the concept of virtual memory. And more specifically, we're going to look at page tables, which is essentially backing all of that. And to give you a bit of an introduction, and also, slowly get into the understanding here, we're looking at a tool I just started, and we're actually going to further the development of that tool, which is meant to visualize what page tables actually are and how they work. And for that, let's get started and look at what I already prepared here. So I just wrote a very rough README today, and that gets you started. So I created this tool called PTViz, a page table visualization tool. It's based on web technology, so we're going to write some JavaScript, or a bit of TypeScript actually today, and we're using the React component library for visualizing our components. But before we get to that, let's actually talk about page tables. So I already started that README pointing you to the article on Wikipedia, and that's what we're going to read first now. Take a peek at. So let's have a look here. When you look up page tables and such, you would usually find references to university courses, or maybe this article to here on Wikipedia. And the way it's usually explained is like, well, you got this virtual memory and you got your actual physical memory, and then there is some translation going on between that, and that involves page tables. And then we would walk you through, hey, this is how it works when you have a virtual address, and it's, various components, so you slice it up, and that's how you translate that to the actual physical memory, and that involves the tables. But that's not how the article starts here, and this is yet just another view on that. So this now starts by looking at an actual process, or program that should be loaded in memory so that it could actually run, right? So imagine you have like all your programs on your computer. They would reside on your, today it's an NVMe SSD. Back in the days, we called it a hard disk, when we had spinning drives and such. But nevertheless, right? So that is the storage that is persistent, and from that we actually need to load the code into the memory that is then directly accessible to your CPU, and that would then eventually hit the CPU's registers at some point, and stuff like that. So we got this big picture already, and so let's take a rough look at how it now actually works when we look at the virtual memory for a process versus the physical memory. Right? So imagine all of that loading has already happened. Your disk or NVMe, whatever, is no longer involved. We're now actually looking at what's in the memory there. So once your application is already in memory, what the operating system here does is it gives the application or the program a view to the memory that looks like as if it were just one contiguous, piece of space, essentially, right? So we have like a starting address here, this is also called like the base address, right? And then from there, we got all of this amount of space here, right? Ending with this address here. Now, that would be sufficient for the program now to run, right? But the problem is, that is not how it physically works, right? So this is just a virtual view now. So the actual data, which came from your disk, has been mapped to physical memory. And because, the problem is you only have like a fixed amount of physical memory, right? I mean, unless you replace some DIMMs or something, but, let's put the idea aside here. You have your fixed amount of memory, and now you need to be careful how you handle that memory, right? So you cannot go beyond that amount that you have. So you need to manage that. And for that, we have some means in the actual hardware. And this is how it works with the virtual memory. So you got all your chunks of memory here. So if you look at those dotted lines here, they would represent a piece of memory. And those pieces of memory are what we call pages. Now your physical memory is also divided into such pages, right? And so what we do here is we map each and every page of virtual memory to a page in physical memory. And that can be any arbitrary order, right? So imagine you're loading more and more programs, right? So if you were just starting, you could just fill the first amount of physical memory and then, continue with the next and so on. And now imagine one of the applications at some point needs to shut down, right? So you actually get some memory back that you could reuse for something else. And now you would end up with a gap somewhere. Or it might be that one of your programs might need just some more memory, right? Because, I don't know, it could be anything. Like, let's say we're editing a picture, right? So, you keep drawing and so on. And, well, what happens is the application that allows you to draw, it would also have an action so that you could go back, right? So you don't actually just store each and every pixel as it is in that moment. But you also, store the history. So over time, you build up more history so that, you could back to where you started and then, I don't know, try drawing some other lines or something. And all of that, of course, requires having more and more memory over time. And, that means we need to keep talking to the operating system and say, hey, I would like to have some more memory. And then the operating system goes and says, well, process, here you get some more memory, right? So yeah, and that's how you gain some, sort of fragmentation over time. And well, but what we get to see here is you actually don't need to take care too much about that in your application in terms of physical memory. For you, you just get some more virtual memory, and that could just grow in any arbitrary way in a way. Like, imagine the virtual address space here is much, much larger than the actual physical memory. But here you need to now do some bookkeeping and see, hey, what pages have I already used, which can I free again, and so on. And to do that sort of stuff, we have the page tables, and that's what we're going to look at next. Well, of course, here in Wikipedia, there is also a bit of a summary, right? So it says, physically, the memory of each process may be dispersed across different areas of physical memory, what I just said, or may have been moved or something to a secondary page, hard disk or solid state drive, the memory technology we have today, as in like persistent storage. And when a process requests access to data in its memory, it is the responsibility of the operating system to map the virtual address provided by the process to the physical address of the actual memory where the data is stored. And now comes the fancy part. The page table is where mappings of virtual addresses to physical addresses are stored, with each mapping also known as a page table entry, or PTE for short. And, well, just to give you some additional information here, there are different sorts of page table entries depending on your processor architecture. And it might also be different even within the architecture. There could be like different so-called schemes, or, there is also like, like on x86, we got these different processor modes, right? So, there is the 16-bit mode, and then you get some 32-bit mode and 64-bit mode. And you can already imagine, right, if you handle different sorts of address space, even though they're sort of, compatible, like, backwards, it still means that, for like the bigger sizes of memory, you would need some different kind of page tables, right? And this is how it works now. So they're describing the translation process here. There is something involved called the MMU, or Memory Management Unit. So that is essentially, the core piece of hardware, that is all around this concept here, that would then look at your page tables. It would look at, the entry point, so the initial page table that you have, right? So imagine it is essentially a tree. So, you have a node that you start with, and then under that, you have the other tables, which would then be the other nodes. Except it doesn't really have to be a tree. It can be a more general graph. And that means, you can technically also have back references. So like, a table pointing to itself again, that, has some ups and downs. There is maybe also other approaches of, handling this sort of stuff. I just want to mention that, so, that you free yourself a bit from the idea that this is necessarily a trait, because it's not necessarily so. And, it also depends a bit on your actual architecture. Now, in this picture here, they already involve the next piece of hardware that is commonly used, and that is to gain you more performance, and that is the so-called TLB, or translation look-aside buffer, which is essentially a cache, right? So imagine when your machine is running and you need to look at the page tables over and over and over again in order to see what's the actual physical memory when I'm given this and that virtual address. And that would be very, very expensive for the CPU to do. So instead of having to do that, there is a little buffer here, the translation look-aside buffer. So when a virtual address is resolved to a physical address, it would first look at the TLB. Hey, do we actually know something about this entry here? Yes, okay, great. And then it goes straight through that and ends up with a physical address. Yeah, in case not, it would actually need to look at the page tables here, and that would say, hey, we actually have a valid entry here, and so on. Right, and then it could go back again and say, hey, this here is the physical address. And of course, it could also be that there is, no backing data actually, so no valid page table entry, and then you would need to load extra data from your disk, well, or NVMe, SSD, whatever, right? So that is the theory, and now this is not, it's not as simple as this looks, right? So first of all, we don't just have a single page table in our modern machines. What we actually already, implied that we actually have multiple page tables. And how that works is through a layering strategy, right? So you can imagine the terms differ a bit from architecture to architecture here, but just generally speaking, you have one level of a page table that is, the very first level that is just one table, right? You always need to start at one point. And after that, all of the entries in that table, they can point to multiple other tables. And those in turn may also point to multiple other tables. And the number of levels, that now depends a bit on like your specific architecture, and possibly, you may choose a certain scheme within your architecture. Like for example, on RISC-V, and in theory, you can choose the scheme. In practice, the existing hardware doesn't necessarily implement everything yet. But yeah, now let's put all those flexibilities aside a bit and look at some more concrete examples here by, going down here. We will skip the translation failure here because that is not interesting for us right now. We don't care about frames. We don't care about everything else. We want to look at the next picture. So let's talk about multi-level page tables, right? So in this example here, we're looking at a very, very simple two-level page table, right? Well, two levels of page tables. And the way this works here is they're calling this level here page table and this level here a page directory. However, you don't necessarily have to call that a page directory, right? So this is, because of history that we had with development of that sort of stuff. People first talked about, hey, yeah, we get the page table, right? And then in addition, they said, well, how about we have multiple page tables, and before that we have a page directory. It sort of happenstance. So you could also call that a page table, right? And in fact, depending on how you organize them, they could actually be very much the same, right? So imagine this here, like the number of entries that you have and what each field in every entry means being the same as here, right? So it's just the same sort of thing. And that also makes it much, much easier for the operating system if you need to manage that sort of stuff, right? So imagine like, every table looking a bit different, you would go nuts completely, right? So yeah, it's actually very important for us in computer science to keep these sorts of things simple. Except, of course, that's not always how it works. And with that, let's look at the second example before we look at how this really works in detail. This is a three-level one. And here, before the page directory, we now have a page directory pointer table, which now is, in fact, a different kind of table. And this table here, really as it is visualized here, just has 4 entries. And, that means you only get like, a few bits to actually represent that, right? Um, anyway, before we dive too deep now, let's see if we get both in view. Right, that works. Okay, now let's briefly look at how it actually works, right? So imagine we're now giving a virtual address and we need to load some data from memory, from the actual physical memory, right? Let's say there is a number stored somewhere in that physical memory, and that number is something we now need to use for a calculation, right? Let's say we want to add two numbers, and one of them, is stored in memory. Now we need to load that number, okay? We have the address to that number, and the address is now the virtual address. And we look at it like this. We take one piece of the virtual address. In this instance here, it is 10 bits, also denoted here by, the slash. This is a very, very common notation in IT. So you get a slash and then, a number, and that means the number of bits, right? So up here, from this address, you get each and every bit, represented by these cells. Okay, so we take these first 10 bits now, and those don't actually mean an address, right? What they refer to is a so-called page number. And this page number is what we now use to look in the first table, well, in this instance called the page directory. And this just tells us which row to pick here, right? So what we do is we just go down the table to the row that is indicated by this 10-bit number here. So it can be anything from, 0 to 2 to the 10 minus 1, right? So that is the range of numbers that we can represent. So anything from 0 to 1023. So we got 1024 entries in that table, okay? So whichever entry we now pick, this will tell us the next table to look at. So this is now very important to understand. This tells us the row in the first table, and now the entry in the table tells us the next table to look at. Which also means, depending on the number that we have here, we need to continue with a different table, potentially. I mean, multiple entries can, in fact, just point to the same next table. That is not excluded. I mean, it could be that there is some architectures forbidding that, but in general, that could happen. But let's imagine it's not the case. So we have multiple entries here, and they in fact point to multiple different tables for the next level. That also means that even though you just got one table here, you may have many, many, many different tables here. So up to 1024 in this instance, right? Because we got 1024 entries here. They could point to another 1024 different pages. But what happens in practice usually is you're not actually using all of those tables at the same time. So that means, some entries just remain empty, which is perfectly fine. Anyway, so let's just continue with how the address resolution works. So we now take the next piece here in the virtual address, again indicating which row we need to look at in this table here, which then finally tells us which page to look at now in the physical memory. And now once we know that, we take the last few bits here. In this case, it is 12 bits, right? So representing numbers up to 4096 minus 1, or 2 to the 12 minus 1, right? So we start at 0 as usual. So the highest number would be 4095, right? Now you know which page to look at here, and you also know which byte to look at here. So those remaining 12 bits tell you which byte to look at in the page that you just found. So yeah, that could be, I don't know, some byte somewhere here. And, as indicated by all the dots here, that just means, you just find the very, very, very specific byte in memory, and everything around you has like lots of data, right? So think of the 16 gigabytes that you have in memory here. So it could be like somewhere right in the middle. So you got like 8 gigabytes before you and 8 gigabytes after you, minus that 1 byte that you just found. Okay, So we got that byte now, and as I was implying, so with our little program that is now trying to just load a stupid number from memory, now we got that address in memory to load the number from, and we finally get it in, let's say a register that we're just loading the data to. And that is what the hardware actually does for you behind the scenes, right? So the operating system does not have to do this lookup memory and then manually and then, scan the physical memory itself. That is now done by the hardware itself for you. Okay, so now putting that example aside, let's quickly look at this here. It actually goes the very same way. So the only difference here is we got a few more bits here, in the beginning. So instead of looking at this table already, now we got another one, which has 4 entries, and then we got 9 bits here and 9 bits there to find the respective rows in the respective following tables. And again, we're hitting the actual physical memory again, by getting the last 12 bits here, and then it gets translated, and boom, there you got your number. So far, so good. Now the thing is, I just explained this very briefly, right? And I do not expect people hearing this for the very first time to actually understand it right away. And that is actually a very, very common issue, right? This is, in fact, not too easy to understand. And even harder is the question now, how do you actually construct these tables so, that you get very efficient translations and also, minding your security boundaries, that everything here is secure, right? So what you do not want to happen is, let's say you got one process and it's looking at, I don't know, somewhere in memory. You must not provide that process with whatever other process's memory, right? So you need to make sure that you don't have an entry for your given process, pointing to memory that is already used by another process. Or even worse, the actual operating system, like the kernel behind it, right? So you do not want to reveal data from your kernel to any random process, right? That would be a huge security violation. And because that is really not trivial to do. We actually have like a bunch of write-ups and still, papers coming out and so on. And that is also what I left in my README. So, I gave some references to like, some computer science lectures and labs and, how FreeBSD documented their findings. They are one of the older operating systems, if you will. They were developed like, starting around the 90s. And back then, people also had to get started, and then the system matured over time. People did write-ups, and people made changes in the memory management subsystem. And of course, the same happened also with Linux, right? So over time, people changed things and so on. So yeah, that's it for everything down here. I'm not going to dive any further. We'll just get back here to the README. And yeah, so as I said, there is this link here pointing you to the article on the FreeBSD website. It's like a blog article, right? So we can have a brief look at that. Design elements of the FreeBSD VM system. Now don't get confused by VM here. We do not mean virtual machine. We mean virtual memory. That is, in fact, also an issue with computer science. We got these colliding acronyms, so you always need to know the actual context. And yeah, in this case, we're talking about virtual memory, right? And yeah, it starts like the title is just really fancy way of saying I'm going to attempt to describe the whole virtual memory enchilada, as they say, and so on, and the swap subsystems, and so on and so on. Then comes a bit of an introduction, also a bit ranting about Windows NT for whatever reason. Claiming they repeatedly made mistakes solved by Unix decades ago. I can't say anything about that, or I'm not going to judge anything here. Just in case you're reading this here, be prepared for seeing that sort of stuff. Of course, they also mention Linux at some point. Let's have a quick search here. Where do we got Linux? Oh, there we go. Linux is a registered trademark. We know that. There. Of course, because people are very biased, right? So yeah, they're saying Linux also makes this mistake to some degree enough that we BSD folk can make small jokes about it every once in a while. Anyway, Linux's problem is simply one of a lack of experience. That is in fact not true. So if you know Linux, then you also know that it's actually the far wider used operating system. There is way more people working on it, right? And they got tons of experience over the years, right? So yeah, there is actually a very, very large core team maintaining all of the different subsystems. And of course, that is also true for the memory subsystem, right? So there is, if you look at the Linux kernel source code, there is one big directory called that is short for memory management, and that's where you would find essentially the counterpart to whatever they have in FreeBSD. I'm not too familiar with that. I just want you to be a bit careful when you read these very harsh words here. It's not always as the author, makes you believe it. So yeah, don't believe what people write on the internet. Funny thing here also, this is an article from the year 2000. So of course, in 2000, the state of the systems wasn't as it is today, right? So Linux was just barely was it started in 1991, I think? So it was just 9 years old, and FreeBSD was, I don't know, maybe 2 years older or something. Yeah, it's a bit hard to tell, how many people or who was actually working on all that stuff back then. So you would, need to look a bit at history. But yeah, in general, just be careful with those words, especially in the modern context. We're now 25, like a quarter decade later. Things have changed drastically, of course. So yeah, everything that you see in here might actually not be, in fact, true nowadays. Yeah, nevertheless, I actually put a link to that article here. And let's actually go make a change to the README, because I just realized that it's from 2000. I hadn't seen that earlier. So we're going to write, bear in mind that this article is from the year 2000, and some, what do we call it? Some things are not as they are not to. Some things differ today from what is described therein. Right. Yeah, I would just drop that sentence to keep it mostly neutral, right? So yeah, again, I don't want to be judgmental here. Remarks, readme, add remark on the FreeBSD article. Alrighty, and let's push it to our repository. Alrighty, so that's gonna appear in a few seconds. Alright, so now the goal of the project I'm doing here is I want to visualize page tables, except I want to do it a bit different from what we just saw on Wikipedia. So what we just saw on Wikipedia is also what they describe in textbooks, essentially. The problem is, so multifold. I would just, point out a few things. So number one, we got static images, right? So you don't actually get to see very much. There is no animation walking you through, how the resolution works, over the few pieces that you have in a page table entry, right? And you also don't see how things actually change over time, right? So everything is just described in text. Number two, that is only looking at one example. However, what we could easily do is, if we develop a very neat application now, we could switch to different ISAs, we could switch to different schemes or, processor modes, like, the x86, 16-bit and 32-bit, whatever modes, right? Which are all a bit different then again. And I was actually thinking about this, brainstorming a bit today and exchanging a bit with a friend who's actually teaching operating system stuff. And so at some point I figured, hey, if I wanted to, I could actually make a bit of a game out of this, right? So I could provide you with a clean state, right? Let's say, we just got started and we're the operating system now, and our first application gets loaded to memory. And now you, the player, you get to write the page tables in order for them to, resolve and, actually copy what the program is describing, and then finally resolve to the actual physical memory. A little teaser here. If you do it horribly wrong, you might end up in a situation where you get into infinity by describing page tables which never actually hit the physical memory, which means, in that case, you would actually get a signal from the processor. You would get an exception or a trap, could also differ a bit from architecture to architecture, what they call it. But essentially, you would get interrupted. And now what you need to do is you need to rework the page table so that the resolution can actually continue. And it might be that you never get to the point where you wrote a correct page table, and therefore you might be infinitely, spinning and spinning and spinning, and that means your kernel is broken. In other words, yeah, so we could make a game out of this totally, and then, play with arbitrary constraints. Like, I don't know, let's say we want you to have like the least amount of pages involved, or the actual physical pages, or the least amount of tables involved, or the least amount of steps involved, or the least amount of page faults, or whatever have you. I haven't mentioned one thing, I just realized it. The question is, where are the page tables actually stored? So, as it is with the common architectures today, the page tables themselves are in fact stored in physical memory, which means that if you're working with physical memory, also in your operating system's kernel, you also need to know where you find those page tables so that you can update them over time, or add new tables and so on. And you also need to keep in mind that, you can technically write tons of page tables, but that is then wasting your physical memory, which is a, very, very important resource, right? So the more of that memory you, in quotes, waste, the less you can use it for the actual programs that you want to run, which is, in fact, why we have those computers in the first place, right? So they're not just for toying around or something. We actually want to do something with them. And, well, our processes or programs today are actually hungry for memory, especially if you know web browsers, right? So you may know that you can look at your memory. Let's actually do that here real quick, right? So here we got the free command, and that shows you how much free memory you have. And you might already guess I don't have much free memory. In fact, just a few megabytes. So here in Linux is free. There is, this column that is called free, and this column that is called available. They essentially indicate the free memory. You got this here shared memory. You got some buffer or caching. I don't even know what they mean in detail, but yeah, you can also use these two columns here, right? So you got your, I don't know, it's 24 gigabytes here. And then, so that is the total memory. And then you got the used memory, which is, again, another almost 20 gigabytes, 19 gigabytes, something, right? So yeah, our processes are hungry for memory. And well, in my case here, I'm, just being very wasteful in a sense. I always have like lots of tabs open in my web browser, so that leads to, using lots of memory. I literally don't have many other processes open, in fact, right? So I got my web browser and I got some terminals, and that is essentially how I use my computer, literally. I mean, occasionally I would fire up a few messengers here and there, like, for communicating with people on Matrix or something. That also takes memory again. But yeah, essentially my web browser is taking most of it, and then I got my few terminal things here. All right, now let's get back to working on the application I started. Let's actually look at, what the current state is. I'll promise you it's not very much. So that's it. All I got so far is, I got some tables here, like this one, and that one, and that one. There is no, application state or whatsoever so far. They're just drawn ad hoc here. And then we got some lines between them indicating that we're pointing to other tables. And I also want to make clear, I got, these different colors here, right? So I got the green color here for reference to the table itself. And then I got the blue color here for referencing another table. And I intend to keep it that way because, in fact, this is meant to also be used for, the development of some operating systems that I'm involved in developing. And I want to be able to visualize stuff to me. So, there is essentially two ways of visualizing memory. So number one is you just print everything out as text, and it's like in fact super hard to understand, because you just see a bunch of text, or you do it visually like here. I mean, of course, there could be other ways. You could also turn them into music or something. But what I'm trying to say here is, I want to have a visual view, right? Which also means that if I were to develop something now over time with the operating systems I'm involved in, I would need to have some mechanism for dumping out some information as the system state, and then also feeding it into here. We're going to get back to that at some point later, because we're frankly not there yet. There is actually ways for doing that sort of stuff. We could even automate it so that you don't need to copy paste things or something. Yeah. And in addition, what I also want to do here, I already teased that, we could make a bit of a game out of this here, right? So I could add some menu bar or something that would let you like choose the ISA, or, I don't know. Let's say you get a menu item or a button that will let you add a new table. And then you could we could visualize like the addresses of the tables, and how they point to each other, or we could even omit the addresses entirely and just take care about the actual numbers, right? So yeah, and instead of so usually a page table entry would have an address inside of it, right? And that address would then point to the next table. That would then again be a memory address. But we could also just give those tables numbers and just be done with it, right? So far, I haven't done any of that. And in fact, I actually have all of the code necessary for doing that, or almost all of it, in one file. So yeah, let me actually open that now, and yeah, I just zoomed in a bit so that you can actually see what I'm doing here. Yeah, I know screen recordings and what I see are a bit different, right? So I know if you might play this on your, I don't know, some smaller tablet or something, you might not be able to see everything. All right, so we're zoomed in. So yeah, the first thing I want to mention here is the framework I'm using. This is the Next application framework. And I just bootstrapped it. So let's actually rm-rf this here. I think it's not even needed, right? So this is still running. And in fact, we got hot reload, right? So whatever edits I do, we would end up with a result here immediately. Great. Boom, boom. Remove boilerplate API code. Yeah, whatever. I might reword the comment. So yeah, that boilerplate code is essentially just generated by running a command to set up such a project. So if you look at the project, this is roughly it. The main thing we're looking at is the source directory. Most of that stuff here is configuration files. Here we got our modules that we use as dependencies. This here is like a bit of boilerplate again. So in public, we got the fav icon. Nothing really to speak of, so it's really just some default icon that is coming from here. We could also replace it over time if we come up with a fancy logo, but who cares now? We got the docs directory. That's where I dumped a first initial screenshot, and we got the license. Well, and that's already it, and you already saw the README. Alrighty, so yeah, let me actually briefly show you the source directory then. So far, we got this here. We got a components directory. That's where we got the UI components. There is one called lines. There is one called PT for page table. And then we got pages here. Now this has nothing to do with the pages we're talking about. So nothing like memory pages. This is the pages like on a website, right? We're actually not doing anything here. So we only get this index TSX file. And then we got some style sheet here, the CSS. So yeah, the index TSX would be, yeah, don't care about this stuff here. Actually, my syntax highlighting isn't really set up here. We might, for further development, choose a different editor or try to fix the setup here, because this is obviously not working too well. Anyway, yeah. So all you see here is just some boilerplate code. So this is really just the main entry point. And then here I'm rendering something called lines. And that shouldn't even in fact be called lines, because that would actually be our app. So let's call this app now, and also import it from something called, where do I get this actually? Here. app. Yeah, let's just move it there. We call this app, and there we go. Now you see this dynamic thing here. That's got to do with what we're doing here. So we're drawing on a HTML canvas element. So the canvas element, allows us to draw arbitrary stuff. Just like the lines we're seeing there, I'm using a library for it, and but the application framework is actually meant to run in this hybrid mode where you could run some code on the server side and also on the client side. You could actually do that with the same code so that you could pre-render things and then just continue with the work on the actual browser side at some point. We don't care about any server environment here because that's not what we're doing. So let's actually close this here entirely and just create a new thing here called app. So we actually need to do this here. So we're going to do app.tsx. And well, what do we do here? So we're going to, this is now, if you don't know JavaScript or, well, TypeScript, what we're using here, this is really just a very, very simple way of, describing our UI components just as simple functions, right? That's what we get from the React library. Okay, so let's also open this lines.tsx thing because I'm going to move some code over to here, and that would then be specifically this here. So what you see there, lines. This is not all lines, right? So they call it canvas here. I'm going to call it something else. So instead of canvas, this will be called app. Actually, it doesn't really matter what I call it because it's just the default export. But yeah, by convention, we just use the same as the file name, right? So we call the file app, and then the default export here would also then be called app, and boom, there you go. Okay, I also got some data here. That would be this here. And I got this bit of styling around it, so we also keep that. And now you realize I'm almost copying everything exactly as it is, except not everything, because everything above here will not be copied. Alrighty, so we got that part, and we're now going to copy that again. Boom. All right, so we got stage. That is coming from the library I'm using. We got layer. That's also coming from the library. We got circle. I'm not using circle. We got line. I'm using line, but not in this file here. So let's remove it there. Let's also remove circle there and layer here because that is not used here. And also stage, right? So we're just using line here. And instead of just defining const here, we're going to say export const. And again, here we're going to say export const. We got PT and PTE. Those are not used over here. We got width that is used here, and we got line height that is also used here. Now, yeah, over time I will also need to move those to another file. But yeah, I'm just doing some stupid refactoring here, so nothing fancy in that regard. All right, so we got this here, and now we also need to have the lines. So far, I have these two sorts of lines. I got the self-reference lines, and I got the lines that refer to a next table, and they just have according names. So we got going to do this here. We got the self-ref line, and we got the next ref line, and they come from lines. Alrighty. Okay, and here you also see like the colors, and that's already it, I think. All right, does it still look good? No, it does not. Oh no, it's complaining about app. Alias relative source app inside of project. Great. Doesn't seem to work. Why does it not work? Okay, I mean, it might be that we need to restart this here, but usually that shouldn't be necessary. But yeah, nevertheless, let's actually, oh, look, now it works. Okay, great. Yeah, sometimes this hot reload stuff doesn't really work, but yeah, whatever. Okay, so I'm going to close this here now, because I don't need it for the time being. And I'm going to add some more Yeah, let's actually commit this already. Factor out main app. All right, we got this. Okay, so yeah, we got the structure now here. We got the file app.tsx. The global starts, they don't really matter now here. Pages don't matter as well. So we got the components, and now we got lines and PT. So one thing I want to add now is, and that is for the page tables. So what you would also commonly find is, let me show you again on Wikipedia. So I already said something like, there could be valid or invalid entries in those page tables. And how do you know whether a page table is actually valid? Well, that also depends a bit on the architecture, and I don't think it's even described here. They're referring to some other stuff here, like write or executable. So writable or executable, that refers to the idea that every page in memory should be either or, right? So you don't want to have the same code to be both writable and executable, because that would mean that you could change the actually executable code. It's a security policy. They also describe it a bit here, like, security policy in operating systems, and you can in fact enforce that in hardware. Alrighty. So what do we see about read, write, execute here? Read. Let's see. Oh, there we go. There we go. There was already something. What was it? There. Some MMUs trigger a page fault for other reasons, whether or not the page is currently resident in physical memory and mapped into the virtual memory address space of a process. For example, attempting to write when the page table has the read-only bit causes a page fault, right? That makes sense. If something is marked as read-only, it shouldn't be, changed. Then we got this here, attempting to execute code when the page table has the NX bit, the no execute bit, right? Then it should be, also be, what is it? Yeah, it would also be causing a page fault. You can already see where this is going, right? So, if your operating system is now going, it's getting signals from the hardware, you actually need to be aware of, what your current setup is, because if you get a page fault here, you get a page fault there. Now the question is, why did you get the page fault? And for that, you actually need to know your page tables and the page table entries, right? Because otherwise you can't really make up a reason for it, right? Let's say you get a page fault and you think, oh, there is something missing, so I need to add some more entries so that I have mapping. But in fact, it could be that your mapping is just fine, but those bits are actually messed up, or there is in fact an illegal action currently going on, and some process is trying to read some information it's not supposed to see, right? And in order to depict this, we're going to see that we add something to our page table entries, right? So far we got just these simple rows, and these rows do not indicate anything, right? So I could now start coloring them or something. So, but what I just want to do is I want to add some boxes here, okay? So what we're gonna do is we're going to, actually close it. Yeah, whatever. Yeah, so we're going to look at the page table entries now, right? So the way I've set this up so far is I have the, I'm actually using HTML tables, right? So I'm using a framework here for doing the styling that is called styled components, and this is how I would then style them, right? So I would go style.table, style.tbody, and so on. And then here again, I could also add some properties. And now I want to be able to say, I want to be able to add some boxes essentially. And the boxes should then indicate whether a page is like writable or executable, whatever, right? Let's actually start with those three simple things. And we will later look at whether that actually makes sense, or, what we need to do for different architectures, right? But we can still draft those components for a start. So what I would call this is a bool box, okay? So bool as in a Boolean type, right? So it could be on or off, okay? Now what this is going to be is a style.td. So that would be for table data. And it will get some properties. So property number 1 is we want to see if it's on or off, okay? So how do we type this? Well, just as Boolean. So we're just going to call this on, and then is it bool or Boolean? I think it's Boolean. I'm not too sure, to be honest. So I haven't done too much JavaScript or TypeScript in quite a while. Anyway, so what we're going to do now is we're going to give this a bit of border, and I just figure I already got some border, but it's on the TD. So I will move this here from the TD to the TR, right? And yeah, instead, yeah, here, so this is where I'm now going to, have a border like all around the TD. Okay, so how do we do this? We just go border, 1 pixel, solid, and then the color. And what should the color be? I don't know, let's pick some red or something, right? So this is RGB, so it would be FOO, like this, right? So now we got a beautiful red border. And what I also want to do is I want to now make use of this on Boolean, right? So I want this to look either like fully red. So red could be for on, and then I could make it clear for being off. So what I will do is I will just use background. And the background is now, it depends, right? So we're actually going to do it this way. So this is now for, using JavaScript code again inside of this saving CSS. So this is going to be processed again by the runtime. So yeah, this is in fact how string interpolation works in JavaScript. So we got our variable on, and now depending on it, so we're going to say on. If it's on, what we're going to output is we're going to say background colon hash FOO like this, and otherwise we just give it an empty string, right? Okay, and now we need to close this again. So we need this here, and that should be it, I think. Maybe I forgot something. I don't know. We will see. But yeah, that should be it. So now we got this ooh, file exists. Add what did I do? Of course the file exists. Yeah, I don't know what happened. Anyway, so now the question is, how do we add this here? So yeah, just for drafting, right? So I could go boolbox. I could close it again, / boolbox, right? And now I could add something to it. Let's say the X for executable. And lo and behold, now we got a beautiful X over here, but we actually lost the border from the other TD because I moved it to the TR, but for some reason I'm not actually seeing that border. Why am I not seeing that border? Good question. Welcome to HTML. I might need this here. No, I do not need that. Okay, so the good thing is web browsers are really easy to develop for because you got this beautiful thing here called the developer tools, right? So what we can now do is we can now mess with everything as we want it. And yeah, let's just grab some table here and look at the TRs and look at their properties, like this border here, right? So, oh look, it is actually highlighting something here in orange, right? And what happens if we give this, I don't know, 5 pixels or something? Well, it looks like nothing is changing. Might be any of the many other possible issues. Okay, what if we make this larger? Let's give it a height of 20. A height of 20. I'm too stupid to type today. Sorry. Huh. Come on. Okay, we'll give it a height of 20 pixels. 120, 200. Oh, look, something is changing now. And yet. So the thing is, those TRs, they do have a height now, right? And they could in fact have a border, but I'm not seeing the border. Is it because I'm zeroing the margin? That should not be the case. I should be able to use any margin. And you're actually seeing that it's not changing anything. And that is in part because, what are we doing here? Good question. Good question. Okay, now we're messing with CSS 101. So one thing I actually want to do here anyway is I want to say display flags. So that would already change a bunch of things. I'll just do a quick refresh here, and boom, lo and behold, we got this back. Okay, great. And what also happened, and that is now a Flexbox thing, you can see that this is now, so the box that we just added is at the very end here. Except that is not really what I want. So what I did here is I applied some style to this TD, but I actually want that to be on the TR. So I want the row to have a fixed width, right? So yeah, this is what I wanted to look like. And now what I also wanted to do is, I still want that X, our box that we just added. I want that to be at the end of it, right? So what I will now do is I will use the flex property. So with Flexbox in CSS, you can do all sorts of fancy distribution of elements. So what I'm now going to do is I'm saying it should be treated as space between. And now the question is, what was the name of the property here? The thing is, I always forget this sort of stuff. So I might now look this up or try to remember it real hard. And so what you got is like, you got the alignment and you got the justify properties. And that is justify content. All right, our content is now justified. Okay, good. Okay, so what I want to do now is, so with that bool box, I want to know whether it's on or off, okay? And so now we need to pass something so that we know whether this is on or off. And I will just call a new property that I just call X for executable for our page table entries. And our page table entries, they are in fact stored in a data structure that is higher than this here. Well, it is exposed here, but it's in the coming from the application are the actual values. Okay, so we got E here. E is a Boolean, okay? So obviously that's all still not really used. And never mind. So this here is a very relaxed environment, right? So we can just define something even though it's not really used yet and so on. And it still works just sort of fine. That's because this is not JavaScript. It's an interpreted language, unlike, Rust, where, you would get compile errors over and over when you do this sort of stuff. Anyway, so what we're going to do now is, I got this value already. It's just called to do something. So what I'm going to do is I will say on is true for the first entry, and nothing happened. Oops. Why did nothing happen here? Good question. So what we're doing is we're passing the entries over to the PT, the page table, okay? And the page table is then mapping all the entries, and for each and every entry, we would then render the respective, the TD, the actual value, and then the bool box. And for bool box, we say on equals e.x. Okay, great. Did we mess this here up? It could be. Let's quickly think about it. So if you look at this, this actually looks very similar to this here, right? So what we need is we need $, we need curly brace open, parentheses opening, another curly brace. Now we say on, it's even declared here, closing the curly here, closing that parent here, just like here. Now we get the fat arrow. Now we use this value It's called on. We use question mark, the ternary operator. In case it's true, we return the first thing. In case it's false, we return the latter. Okay, looking good to me. What is wrong? What is wrong? Well, can always refresh, but yeah, I wasn't expecting that to change anything. So let's actually have a look here. So I'm sorry. So I'm adding this for the first entry, right? So that one here. So I'm actually expecting the first row now to have the red background. So let's see what happens. So we got the TD here, we got that one here. So we got border, but we do not see the background. We just got the inherited background color, but nothing else. Okay, and because this is a very great environment, we can do the following. So what we can do is we can just we can declare a full function here, and we could just print. In JavaScript, we don't use print. We call it console. So we got the console.log function. We can just go and do a string interpolation again. Is that how it works? I haven't done this in a long while. We're just logging whether it's on or off. Okay, so what do we? Ooh, we get lots of undefined here. In fact, we get undefined for everything. Okay, so that means our data is not ending up here. This might actually, in fact, be fine. There is, just as an aside here, there is even a tool that we can use to visualize each and every one of those components individually and, you know, develop them over time. It's called Storybook, but I haven't yet set it up here. So yeah, we're doing the, you know, just very simple way for now. Actually, the other way it might even be simpler, but yeah, whatever. Okay, so what happened? So we got our entries here. Right, the other thing we can do is we can also turn this into a full-fledged function. And instead of doing a direct return, we just do this here. And then we console.log the entries here and see what we get, right? And what do we get? We get val to do. We get on true. See that? On is true. Oh, I know, because I called this on and not X. There you go. That's already it. That was it. Can undo this part. Can undo this part. There you go. Sometimes it's really that easy. So yeah, I'm essentially remapping, but on purpose, right? So I want this to have like an X, I want this to have a W for right, and so on. And boom, lo and behold, now it's a red background. Excellent. We could now do the same thing here with, let's say this is for read, right? So let's go R. So we go, hang on. Oh, the declaration was wrong even. Whatever. So yeah, let's go R. So we got readable and executable. That's a bit stupid. We also got an X here, but this is for a point, right? So we got X and Y like coordinates. Anyway, so we're going to do another bool box. Should we actually also make the color a property? I feel like it should be a property. So we got on here, or maybe not. Maybe we'll just choose a slightly less aggressive color. That could also help. Let's say we just go FFF, right? So it could be plain white, except then we can't use white on white for actually writing. So we might actually need a different color. Some nice color that is like suitable for both black and white. What was it called? It's just color, I think. How about we just choose the color in the middle, which would be like 888. The sort of gray. I don't know. It looks very ugly for now, but whatever. It just, you know, I think the red was just even worse. Yeah, we're not discussing aesthetics here now, right? So we're doing design work, but we're caring about functionality now, right? So we go functionality first, and everything else is for some other day. You know, the domain here is already complicated enough. Anyway, so we got one bool box now, and the other one will be the R. See how easy that is? Now we got read and executable. Except, oh no, what happened here? Now we got this thing in the middle, but I would like to have all the boxes by the end. So what we're going to do is, instead of doing this in a TD, I will use a TD, but not like this here. So what I will do instead is, I'll just use a wrapping TD here, right? Whoop. So this TD here now means the flags. We could also do this some slightly other way. But yeah, we'll just keep it simple. And instead of using TD here, I would just call it a div because, you know, it is that easy. And boom, there we go. Now we got both of them by the end, except now they are on top of each other. But we don't want that to be. So what we're doing here is... What could we do? We could also just use our TD element here, right? So we could go TD/TD like this. Okay, so now we're using the same TD element, and now we could go and say whatever we show in a TD, we also go just display flags. Boom. There we go. Now they're next to each other and also got a bit smaller. And yeah, we also got a bit of margin. Except that's not what we declare here. Yeah, we actually defined some padding here. Okay, it's not margin, it was padding. Are we happy with this? I don't know yet. I will have to see a bit. Yeah, I think it's good for a start, but now the problem is, you know, it is already getting very, very dense, right? So, I mean, besides this R here being a bit hard to read, let's actually zoom in a bit, right? So yeah, but you can see where I'm going with this, right? So yeah, it's getting very, very dense. So the first thing I want to do here is I will give these, where is the div now? There we go. Okay, I will go and give this a fixed size. So I will give it a width of, let's say 12 pixels. No, 12 is not enough. Let's actually go 16 and the same with the height. Height. Okay, great. Now what else do I want to do? I want to have centering, right? So I could also use a flexbox thing again, and you know, use that for centering. I can also go with a text align center. Boom, now it's also centered, except not vertically centered. That is, again, frankly, something we can easily do with Flexbox. So we're also going to go display flags. We're going to go justify content will be center, and align items will be center as well. So align items, so that is orthogonal to your flow. So in you know, in Flexbox we got the flow direction. The flow direction is what is the where the justify content is applied. So in that direction we're centering. So we're just you know, flowing in just the horizontal direction, if you will. Except that's not the terminology used in Flexbox, but let's put that aside. we can use that simplified view now, and the alignment would then be, you know, from our point of view now, the vertical alignment. And lo and behold, that's how it works. Awesome. Okay, so yeah, the good news is I still apparently know some web development. Okay. Now it even looks a bit better, even if we are zoomed out completely. Okay, so, but you might know this looks a bit odd here, right? So there is some spacing here, like at the top, but the bottom looks a bit weird. And that is now, you know, now we do some pixel calculation. So I'm giving this a size of 16 by 16. I'm giving this here a fixed height of 20 pixels with a padding of 3, right? That is a bit too much here. So we're going to do this here instead. And again, here, what I want to do is I also want to justify the no, I also want to have the alignment. So even in the TD, we're going to use, where did it go? Where did it go? Where's the other? There. I'll also use align items and do the centering. So our to do here also goes to the middle. And now I want to have a slight panning from the left. And there is another option for doing this. I could also just do it in the TR, right? So I can go padding left. I'll just go padding left and give it, I don't know, 3 pixels. And boom, it doesn't look too horrible anymore. I'm actually okay with that result for the time being. Yeah, good start. Whoops. Yeah, so this is now zoom level 0, so essentially as you see it, and yeah, but you can already imagine we will need to play with that a bit. I also want to do one thing. So you see this height here. That is the height of the, yeah. Let's actually do it a bit different. So while I'm talking here, I'm figuring I want to put this here. I want to give this a height of 100%, so all the height that we can take. But I still want to have the 20, except I don't want to put the 20 in here, but I want to take it from somewhere else. So, you know, I already defined the component here that is called lines, right? So, source component lines, and they also need to know the height of a row, because that is how I draw the lines, right? So I need to know where the line needs to hit the row. And this is why I got the line height here, okay? So what I will do is I will go export those numbers. So yeah, I can either put them here or in PT, or we just introduce another file. Let's go. Source components. We just call them cons.ts. Doesn't really matter too much. Okay, so we're going to import width and line height from star at components consts. Yeah, and we're going to do the same here. Yeah, this here is just a shorthand I've set up for this project. It's actually also what the next application setup does for you. So it will ask you, hey, do you want to have like a prefix for local components, so that you don't need to have like relative paths over and over again, because frankly, that is a bit nuts sometimes. Yeah, whatever. It depends a bit, right? So it can be very sensible. Like, let's say you have a component that has, you know, a lot of files involved. Let's say you have a very complex component and it involves 5 different files, right? And now within those files, they're just relative to each other. You probably don't want to use this absolute path addressing. So absolute in the sense that this is now the same as writing src, right? So you don't really want to have that. There you would probably use relative paths. But yeah, here I'm now for the time being doing this here. Yeah, whatever. Anyway, so okay, we got height, line height, and width would be, whoops. That would be width px. So in HTML, or well, in CSS for HTML rather, we always need to use units. The only exception is where you got size 0, you can just write 0, but otherwise you always need some unit. Can be px for pixels, it can be pt for points, or there's like em and rm and whatnot. Whatever, we're just using pixels here. That is easy for us to calculate with, and lo and behold, it works. Okay. So yeah, and now what I could theoretically do is I could always change those numbers, right? Like, let's say I want to make those larger, it just works, right? So it's scaling very well. So both the lines are scaling and the size of the table is also scaling. Maybe it even makes sense to use those 250. I don't know. We'll have to see. We can do the same thing here with the line height. Let's say instead of 20, we use, I don't know, 40 or something, right? That should also work. And lo and behold, it actually does, except, you know, one table is running into the other. Yeah, that is because of the positions I was using. Yeah, I might just, I don't know, move it further down, and yeah, it's fine again. Whatever. Yeah, but let's actually undo this here. I just did this to show that, you know, the scaling actually works as intended. I don't know, maybe 24 actually makes more sense. Then we could use a slightly larger font and make it a bit more legible. Anyway, I think this is good enough for a start. Let's zoom out again. Okay, good. Alrighty, and I think that should already be it for today. And yeah, we're going to continue this some other time, or you know, I will still need to think about like, you know, where I'm going with this, and yeah, how to actually define this data here dynamically and so on. You know, so far we're just using some super fixed numbers here, right? So all of the points that you see here, so all of this is now fixed entries. It's not coming from any sort of application state. But yeah, I mean, we could technically do this, right. So what we could do is we could already generate this here, right? So yeah, instead of calling this points, I could call this tables, right? And now each and every table, you know, would get its coordinates, and then it would get the, I don't know, its own entry. So currently, as you also see, entries, I'm always, you know, using the same thing here. So of course that is not how it actually would work. Yeah, I would have to do that a bit different. And also what you see here, right? So these points are the same as these points here, and they have to be, because what I'm essentially doing here, every point would be the top left coordinate of you know, each of those tables. And then relative to that, I can calculate everything else. But yeah, I need to know where the table actually is, right? Yeah, there's not really many ways of doing this sort of stuff. Should we? We could, instead of points, we could actually already call this table trait a yeah. A table would have these a table would have coordinates, right? So a table could have something that's called position. We could actually make this an array of PT. Let's do it that way. So we're defining a type PT that has a position, and that would be a point. Okay, except point is not yet known here. We actually need to import that still. Why haven't I done yet? Why have I not yet done that? Okay. See, we're still going here. Anyway, okay, so we got position as a point. So what that means is we need to go point like this. Like this. It's just loading everything a bit here, but whatever. You know, at some point we don't even need to write this stuff here, because it would just be kept in memory for us, and you know, we just need to define the types at some point. And all of these numbers can, in fact, of course, be generated, right? Okay, so we got this here. No, not point. I want to call this pause for position. See, I'm already getting confused. Okay, and now what we're going to do is we're going to iterate over the tables. So we're going to say tables.map, and now map will get a function which has the arguments and the function body, except we're not using a function body here. We're just doing this. Okay. So each page table, well, page tables, frankly, also have a page number, right? So we call this a PN. What do we call that? What do we give that? Let's just go 1, 2, 3, 4. Keep it simple. Okay, so we got page here, and instead of calling this .0, this is now p.pos. Okay, entries is still fixed, so at some point that will also end up here. How about pn? Pn is a number. Okay, so we're doing this here, and now all of this here can go away. Neat. Okay, now we need to do one more thing. So what React wants you to do is, if you output an array like this here, you also need to define a key. And that's already where we're going to use our page number now. Okay, and now these here, we will also define those as data, right? So those would usually actually now be the entries, right? So what I will need to do is, once I know all the page table entries, then I can draw the lines. So, you know, currently they're just defined out of bound, if you will. So yeah, do I really want to do that now? Or do I just want to go and say, I know. Okay, so what we're going to do here is, I'm going to define an array of page table entries, okay? So I would just go and say PTEs is an array, okay? And that would be an array of PTE now. So we got PTEs, okay? That would be an array of PTE. And instead of hard coding it here, I will now hard code it there, okay? So this is now what is going to be our application state. And as you can see, it's already hard to write that in a single row, but we're going to do this nonetheless, just for a start. And yeah, I will use, instead of val, what did I even call this? Yeah, instead of val, we will call this pn for the page number, okay? So I will also do that here. And I will go, page number is, let's say this is a 2, okay? And then we got x true. And now we could provide a few more of those. So we could have the page number 3, and instead of x true, we go r true, and so on and so on. And now those here would also need to be generated. And for that, we need to transform those tables here. So the first thing I'm gonna do is copy this here. Okay. So yeah, we're just starting with the same thing. So we're now just we now just got 2 entries each. And what do we want those to? So they would need to point to other tables, right? So let's say, so this is pointing to page number 2. Oh, right, and we want one back reference. So, okay, so this should be the self reference, and that should be reference to the next table. Now that would be the self reference, reference to the next table. That would be the self reference, and again, a reference to the next table. Okay. And we actually had the those 2 tables were above each other. So those coordinates, they would also need to be calculated at some point. And what happened here? Something got wrong. Copy paste error. Uh-oh. What happened here? There. Alrighty. Let's align this a bit so it's a bit easier for us to read. Okay, so now this would also be the self-reference again. And in fact, we wouldn't have any other reference, right? So the last table wouldn't have any other references. In fact, I will just go 0 for an undefined reference, and that's in fact also how you see it often enough in hardware, right? So an empty entry would essentially just be a 0. That would just work. Okay, so that works. Yeah, but I would also do that here. And now I would also want another pointer here to this thing. Okay, and now we need to map all the tables so that we can calculate all the lines that we need to draw from one table to itself or to another table. Okay, so instead of doing page table visualizations, we're now doing a bit of computer science 101 algorithms and stuff, and transforms is essentially a very core piece to software development anyway. So all the time we're just transforming data essentially. If you ask Lisp programmers, it's like, whatever else would they do? Nothing, right? So everything is just transforming data. Like data is everything in Lisp. But yeah, it's frankly very much a good model for many, many things. Okay, so we're going to say const self lines equals tables.map. Okay, and what we're doing now is for each and every table, we already do some, this is called destructuring. So we get our PTEs, okay? And we also need to know the page number here, okay? So what we're going to do now is we are finding all the entries that are pointing to the respective table itself, right? So we're going to say ptes.filter, okay? Now we're filtering, and now we need to do some horrible things here. So this will also be a function again. Now we got pn. The problem is we also got a pn here. Oh no, what do? We rename the pn. Whoops, sorry. So this is now the PTE pn. In JavaScript we use camel case, not like in Rust we would do this here, snake case. Sorry about that. Okay, so we're going to filter every reference where PTE pn is the same as, and we're using the triple equals here because it's JavaScript. There is double equals and there is triple equals, which is like including the type and such. Okay, so where each and every pn is the same as the PTE pn, and that's actually already it, but we need the position as well. Hang on. Oh, right. So what we need is for the self-reference, we need to know the number of the row, which is indicated by this here, just called I. So the index of the row, that is a self-reference. So what we need to also have is, and I think we should also have that in, oh, right. There we go. So besides the actual entry, we also got the index here in the table. Oh no, we don't want to know the table, we want to know the table entries number, okay? So we got the I. Oh, interesting. Okay. So we're okay. So first we're filtering the page table entries, and let's actually make this a bit more readable. So we're doing this here. Ain't that awesome? That's what you can do in JavaScript. Okay, so this is how we filter. Okay, and now we want to map those entries, and what we want to have is essentially just the I for yeah, we just want the index. So we would have the PTE here, and we would have the index. Except, of course, we need more parentheses, and we just take the I. Okay. So now we got the number, and now we also need the coordinates, right? So we are now back to the level of the page table entry. Okay, and this is where we got the page number. Okay, and we got the position. So we need the I and the position. How about this? Yeah, you need these extra parentheses because we're creating an object now, not a function body. That's how you distinguish them. Okay, so we got the position and the I. Okay, and then we can flatten the whole thing. And yeah, if I'm not mistaken, that's actually correct. This is not test-driven development, right? We're YOLOing the stuff out of here. All right, so we go self lines dot. Actually, I want to call this self refs. Who said lines? Okay, self refs dot map. Okay. Now for each and every reference, what do we got? So we got the position. Okay, and we got the index. It's just called I, and we map it to a self-ref line where the self position is the position. The I is just I. Okay. And again, because we're doing a map here, we need a key. The problem is I could now use this here. Yeah, we'll just call it K and say key equals K. Awesome. So in theory, this could already work. And how about this here? We're taking care of that later. Let's just move that down here as a comment so that we keep in mind what this needs to look like. Let's see if it works. Of course it doesn't, because something went wrong. Okay, what did we do wrong here? This here. We got you. We got you. Where is the syntax error? Parsing ECMAScript. Source code failed. Oh no. Okay, but this is on line 42. You know what that means? It's the right answer. Okay, what is wrong here? Okay, so this is how we denote an element, right? That looks good. What we could do instead is we could just write, I don't know, null or something, right? Is that syntactically correct? No, it is not in fact correct. Okay, I see why. Okay, we're missing more parentheses here. Boom, there we go, fixed. Okay, now we got all the self-references, and now we want to have the references to the other, like those here, right? The ones that, those. So those are invalid references, and those are the references going to the others. All right. Yeah, these entries here, they will also change at some point. So at some point we will use the p.ptes, but yeah, we would need to transform that still. Bum, 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 bum. We're actually writing val, right? So instead of val, we should really not use val. We should write pn for page number, which means this is now effectively gone. And we're actually removing this here. Oh no, I'm so sorry. Instead of that, we're gonna use the p.ptes. Does it work? Yes, it does. Look at that. We now got the multiple entries. And you can also see, different tables got different numbers of entries here. But that is just because of our data. So what we would really need to do is, at some point, if we really want to visualize a whole table, that is now the problem with the visualization, we would actually need to write, let's say we have a 9-bit, piece of page table, a 9-bit piece that would go and indicate the page number. Now we need 512 entries, which is far too large for drawing it on a screen, right? Let's say you got a 1080p screen that would leave you with barely, not even 2 pixels, because you got those things here. You can't even use 2 pixels per entry, and that wouldn't make sense, right? So we will deliberately need to indicate where page entries are, or page table entries are in fact unused. Like here, where there is a 0, we could just filter those out. And if there is, a continuous amount of them, we could actually go and, put some dots in there and just, indicate. I mean, we do got the, we know which row it is, right? So we can indicate like whatever, like this is entry number n, whatever. But that would make the calculation with the lines again a bit harder. Or would it? It would. Oh well. Let's close some things here. Okay, so we're just left with this here. Okay, so const next refs equals tables.map. Again, we would need to flatten the table in the end. Okay. We're doing the same thing here, except it's just the opposite logic, right? We just say wherever the page table entries page number is different from the so the page number now indicating the next table to use, where it's different from our own page table's number. Okay. And now we're going to map this here. Can we actually map it the same way? No. No. Oh no, this is even worse. Okay, now it gets a bit tricky. We have to look at all the other tables in order to figure out which one has the page number that we're pointing to here. That would be a bit inefficient. I mean, we're just gonna do this here now, okay? Okay, so I don't need to know this here. I just need to have the okay, I do need the page table entry. Now for each page table entry, I need to look at the page number, okay? So the pte.pn, okay? And what I'm going to do now is, this is a bit stupid, but I'm doing it anyway. So I will go tables.find. I will go find the table that has a certain, that has the given page number, okay? So I'm going to say P for, no, T for table, okay? And wherever t.pn is the pte.pn, pn. Huh. You know what? We could actually do that here as well, so that it's a bit easier to read. Oh, look at that. It's less code, which is good. Yeah. We can reorganize these lines in a way at some point. Okay, so we are... Let's also do it here then. Oops. pte.pn. Okay, so we're finding the respective table where the page number is the same as this page number. Now this could in fact in turn undefined if that table does not exist. So we would need to add some checks here. But we're just YOLO-yeeting it here, so we don't care. I just need to know the position of that table. And I need my own position. Hoops. Okay, right. Okay, where, oh, the funny thing is, I mean, we do have our own position, right? Okay. So for each and every page table, we're doing this here. Okay. We're using a full function body. We're saying const next pos equals this, const self pos equals pos, and then we return self pos and next pos. Okay, and that's in fact also how we denote it here. Oops. We also need to know the row of the page table entry again. Okay, so we still need the I here. So we need this here. I. That goes here. I. Okay, we got that part. Does it look good? It should. Whatever. So we're doing the same thing here, and except we're going to say, oops, next refs.map. Instead of pos, we got self pos and next pos. Okay, and we're doing this a bit different here. So instead of doing this, we're doing this. Okay, so for, or we call it just R, and then we just go dot 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 R. Okay, let's see what happens. I need a better setup here with the formatter and everything. Okay, so so far it exploded. Why did it explode though? So what this here means is I'm just destructuring the whole R thing, right? So R would be all the properties that I have here, and they would actually be called self pos, next pos, and I, just like the API here. Okay, and that would be the respective position here. So this is the own position, that would be the next position. But yeah, as I said, it could be that this table is not found. So if I mess up the numbers here, it should actually explode, right? So this should exist, right? Let's remove that part already. Whoops. Okay, so again, back to developer tools. Great. What's going wrong? Simple start. We're back to something working. Receive true for non-boolean attribute on. Yeah, whatever. We'll take care of that at some point. Whoops. Okay. So we got this here. We're going to comment this out for a start. Okay. Okay, so this here is having an issue. Could be syntactically, could be semantically that there is an issue here. That looks, oh, wait. Oh, that looks okay. What might be the issue here? What might be the issue here? Okay, we're doing the following here. Instead of this here, because this is a potential issue, right? I mean, we could also just we could factor this out, write a small test around it and stuff. But I don't actually have testing set up here yet, do I? What does package.json say? Do we have a test command yet? No, we do not. Horrible me. I might set this up at some point. There is a bunch of testing frameworks, like Jest, for example. That's the one I'm familiar with. I'm not sure if it's the latest and greatest thing to use. We might actually look at the Next.js documentation to see whatever else they would recommend nowadays. Anyway, so this is algorithm 101, right? So this here should be just fine, right? Because that is essentially the same as here, just with a reverse logic. Oh, I see where this is going. Hey, look at that. We actually already ran into this case where a next, well, this is technically, this is a next table it's pointing to, but table 0 does not exist, okay? So I'm adding a new constraint here to make this a bit simpler. And pte.pn is not 0. Boom, fixed. Except I'm not seeing the lines, but we also commented that out. So let's uncomment that again. I'm not seeing lines. Where are my lines? Okay, so what we're doing now is we're console. Did you know that there is console.table? Now you know. This is what we got. So we got 3 entries here. We got self position, next position. We got the I. So it would be 0 here and 1 here. We even got the coordinates, right? So we got next position and self position and so on. No, so this I here is actually not correct. Like I would expect the line to start here just from the data I've given. That can be fixed still, but nevertheless. Indentation is hard. Oh, this is not a self-ref line, of course. This is a next ref line. There you go. Fixed. How awesome is that? Yeah, no, only the indexes are wrong because this I here must not come from here, right? Instead, it needs to come from so this is not for this was the I for where we're drawing the line to, but that is not what we want. we want to know where the line is coming from. So for each table, wait, what? Is that not it? Oh, right. Okay. No. Huh. Huh. Oh, yeah, I know. Okay, so we did this here. We did some filtering. Okay, so our indexes are shifting, and that is a problem. We don't want index shifting. We do not want our index to be shifted. And that's why we got index 0 here now. Yeah, not great. How do we get the correct index back here? Any ideas, anyone? Actually not checking whether there is anything happen in the chat or something. So yeah, please forgive me. I will just check Twitch at some point later. Or should I do it now? I know, it's just stealing some memory and bandwidth for me, so I'm not doing that right now. In fact, I was just talking to myself, not checking the chat in any way. And I'm very sorry about that. But yeah, if you're watching the recording on YouTube now, you could also drop your thoughts here. Yeah. Again, so like algorithms 101. This does look fine now, except for this minor detail that we're missing a reference now. So what we could do is, and in fact, this is also not correct then, right? So this could technically also be a different row. It's just coincidentally the first one now, because the self-reference is always the first entry here. So what I would want to do now is I will add the respective index here, or should I? Oh, you know what we can do? This is gonna be terrible, but we're doing it anyway. So we're just going to do another map in between, okay? So what we're gonna do is for each and every PTE, come on, there we go. We're gonna go .pte and we're adding the index. Boom, we saved our indices. It's not the most efficient thing to do, so you know, we could already do it here, but whatever, that would be an issue for the application state later or something. So what I want to do is I want to have that here as well. So I will go ptes.map before the filter, like this. Okay, and instead of taking the I here, there we go. So for each page table entry, I want to get the so there we go, position and the index. Okay, just like that. Awesome. Okay. And now we can do the same thing here. So I would be pte.I. Except, of course, that's not how it works, because something always has to go wrong. Okay, what happened this time? The problem is, I don't know what's wrong here. That must be a framework issue. We're not seeing much feedback here, right? And there's nothing here either. That is very, very sad. That is very, very sad. Anything wrong here? Okay, so what else we could do? Well, we change a bunch of things, right? So the first thing we're doing here is this here, just to see if the first part is correct. Apparently not. So we're doing this here. Okay, good. So the issue is with the self-references, and this is wrong. This is wrong. I see, I see. Okay, so we're missing the I here. Okay. Where did the lines go? Now they're all gone. Dear. Oh dear. Whoops, sorry. Okay, so we're mapping the page table entries to the respective page table entry and the index. We're then filtering and then mapping. It looks good to me. Okay, let's just do a reload and let's see what this this gets us. This still looks a bit wrong. Oh wait, no. This is the number of the table. We don't want the number of the table. We want the number of the page table entry here. Okay, now this looks much better. Okay. We are going to change this into empty array again, just to see if we get those back, and they look good. Okay, good. Okay. So now this is already a bit better. The filtering logic also looks good. So we take out the position, and we take out the I, which is the index that we just added. We flatten the whole thing, and we got the, oh, how about we actually log the self-refs now, shall we? Oops. Oh, look. Why is the position always undefined here? And why is the I always 0? That is apparently not correct. That is not correct. Let's just do some logging here. Then explicit return there. Console.info. Info. So we'll just call this here PTE and go const equals PTE. And we're seeing this. Huh, interesting. We don't have the position. Where did the position go? Oh, right. So the position, It's not in the page table entry, of course. Of course not, of course. So we need the position here. How about now? Now it works. Awesome. Alrighty. So we can remove this here. Put this, whoops. That back here. That back here. There we go. Remove the console log. And it looks nice and shiny. Alrighty. So what are we going to commit? Git status. Look, we did a whole bunch of stuff. Oh, look, there is an empty space here. My OCD wants that to be removed. Where is it? In the bool box? Okay. That is in PT. There we go. Git diff. Okay. Git commit. So we have extend PTEs with RX bits. We calculate the lines, right? That's essentially what we do. Of course, we need to add the const file. Git commit -a -dash amend -dash no edit. All right, so this is what we've done today. We removed some boilerplate code, which is sort of empty code anyway. So we factored out the main application here, yada, 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 just moving some code around. And then we extended the page table entries. So we added these bits R and X instead of hard coding everything here, like the references and the tables and so on. We're just calculating them. And I mean, we also factored out the width and line height thing, but whatever, it's just minor details. And that's already it. That's it. Git push. All right. Now, eventually, this shall be it for today. So if you want to follow along here, or you just want to do a recap or something, check out the repository. So this is on GitHub, and never mind this line here. This is on GitHub, the platform system interface, that is the org or organization, and then PTVis, that is PTVIS for page table visualization, that is the repository. And you should be able to just set it up. I put the notes down here. So essentially what you do is npm install and then just npm start. It's just, JavaScript project 101. So if you know JavaScript, you know this sort of stuff anyway. Otherwise, yeah, I hope you like this. I will see you again in some of the other streams that we do here. Have a great time. Until then, goodbye.